Okay, we continue to learn Chapter 3, Vector Space. Section 4, Basis and Dimension. So the first part we consider about basis. A spanning set for vector space is minimal if its elements are linearly independent. And the minimal spanning set form a basis for a vector space. This is the definition for basis. The vectors v1, v2 till vn form a basis for a vector space V if and only if the first condition v1, v2 till vn span the whole space V, and secondly, v1, v2 till vn are linearly independent. Okay, we see some examples for the basis. The basis for R3, for example, the simple one, E1, E2, E3, if you choose the coordinate vectors, of course, they form a basis for R3. And others, for example, you can choose this set of vectors or this set of vectors. Okay. In order to check whether they are bases or not, you should check if they can span R3, if they can span the whole set, and if the vectors in this set, they are linearly independent. Okay. Now we consider the basis for matrix space. So we consider R 2 by 2 matrices. So if you consider E11 is this matrix, only the 1, 1 entry to be 1, other entries 0, and E1, 2 is only 1, 2 entry to be 1, others to be 0, and E2, 1 is only this entry to be 1, the 2, 1 entry to be 1, and others to be 0, and E2, 2 only the 2, 2 entry to be 1, and others to be 0. And it's easy to show that using the definition, they are linearly independent. And also, each matrix, each 2 by 2 matrix can be written as a linear combination of these 4 matrices. So these 4 matrices constitute a basis for R 2 by 2. Okay, now we have this theorem to consider the size of basis. Okay, if V1, V2 till Vn is a spanning set for vector space V, then any collection of m vectors in V where m greater than n is linearly dependent. See, here you have n vectors spanning the vector space V. This means any vector in this vector space V can be written as a linear combination of these given n vectors. And if you have more vectors m greater than n, then these m vectors must be linearly dependent. This means there must be some vector which is unnecessary. Okay, let's see the proof. We show it. Let U1, U2 till Um be m vectors in V, where m greater than n. So we have more vectors than the number of vectors in the spanning set V. Since V1, V2 till Vn span the whole space V, we have Ui equals AI1 V1 plus AI2 V2 plus till plus AIN Vn for all I varies from 1 to till m. Okay, because it spans the whole set, of course, any vector in this space can be written as a linear combination of these given vectors, right? And in order to corresponding I, each I equals 1 to m, we give the coefficient here as AI1, AI2 till AIN. Okay, and then you can find a linear combination of U1, U2 till Un, like C1 times U1 plus C2, the scalar C2 times the vector U2 plus till plus Cm times Um becomes this expression. See, C1 U1 plus C2 U2 plus Cm Um. You just substitute each Ui here in this expression, and then you can find it as a summation. First, I varies from 1 to m. Ci times Ui, where Ui is the summation of this Aij, Vj, where j varies from 1 to n. And because they are finite sums, we can change the positions of the two summation. So it equals summation j varies from 1 to n, summation I varies from 1 to m, Aij, Civj. So we can write it as a summation of this scalar times these given vectors, n vectors Vj, and do this summation. We consider this system of equations. We consider it's the coefficients here, right? For each coefficient is here. So summation I varies from 1 to m, Aij, Ci equals 0. For j varies from 1 to till n. So this system, see, is an underdetermined homogeneous system. It is homogeneous system because the right-hand side are all 0, and they are underdetermined homogeneous system. Underdetermined because here you have m greater than n. So you have n equations, but you have m unknowns where m greater than n. So this is underdetermined system. Okay. So by the theorems we learned before, we know that there must exist free variables, see, and it must have non-trivial solutions. Clear? Because there are free variables, and then must have non-trivial solutions because free variables can be chosen arbitrarily. Okay, so say C hat 1, C hat 2 till C hat m is a non-trivial solution. So there exists such non-zero solution, not all 0, such that this coefficient equals 0 for all j, varies from 1 to till n. And then this means C hat 1, C hat 2, C hat m, we substitute there here, they will be 0. See? This means there exists non-trivial solutions. C hat 1, C hat 2 till C hat m, such that this linear combination of u1, u2 till um equals 0 holds. So these m vectors, they are linearly dependent. Right? Non-trivial solution corresponds to linearly dependent. Okay. We continue to consider about the size of basis. Okay. This corollary. If V1, V2 till Vn and U1, U2 till Um are both bases for vector space V, then we must have n equals m. See? Because they are both bases. Bases means they can span the whole set, whole space, and also it is a minimal spanning set. Right? A minimal spanning set. No vector is unnecessary. So if these two set of vectors, they are both bases, then you must have the same number of vectors in these two sets. Let's prove this. Okay, let V1, V2 till Vn and U1, U2 till Um both be the basis for this vector space V. Since V1, V2 till Vn span the whole set and U1, U2 till Um are linearly independent because it is basis, they are linearly independent. It follows from the previous theorem that m must be no more than n. If m greater than n, they are linearly dependent, so we must have m no more than n. And the same argument implies that n is also no more than m, right? Because u1, u2 till um span the whole space, and also v1, v2 till vn, they are linearly independent. So we have n is no more than m. So these two directions, these two implications imply that n equals m. So all the bases of V have the same number of vectors. So as long as they are bases for the same vector space, they have the same number of vectors.